Welcome back, my structural analysis friends. In the last couple of videos, we've been talking about virtual work, and we've talked about using the technique for both trusses and for beams. In this video, we're going to turn our attention to more complex structures such as frames, and I'll show you how to do that starting now. So without further ado, let's get started. Solving deflections for frames can be a little bit intimidating when it comes to hand calculations, but using the principles of virtual work that you've learned in our previous videos, I can show you the basic equations and how simple this technique really is. Now, before we get started getting into virtual work, we've gone through the derivation of the parts of the equation that are needed for frame analysis back in our previous video. So if you haven't already watched the virtual work for trusses section, that's where the axial load equations come from, or the virtual work for beams video, that's where the flexural equations come from. You might want to do that before we move on any further, but the techniques herein are very similar to what we talk about in those two methods. All right, so everything boils down to, just like before, what we had with the virtual internal work calculations. All right, and so we know that for beams, okay, or for bending effects, we knew that it was the summation of the integral of the virtual moment times the real moment over EI dx. So that doesn't change. And then for the axial effects, which came out of the trusses, it was the sum of what is now the integral of FEF L over AE for those particular calculations. Now, most of the time for axial load, it's not an integral, it's a constant, but just in case for the math, we'll stick to that. Now, if you remember when we set that equal to the, particularly in the beam video, when we did our deflections equation, that for beams it was the sum of the integrals of all of the moments. Well, now all we're doing is we're adding the contribution of the axial load to this deflection as well for the frame, because an axial load in one member can cause a deflection in another because of the way that the structures are connected. And likewise, in beams you had a 1 times the theta equation. Well, now all we're doing is 1 times the theta and doing the axial effects here plus the summation of the moments. Now, in most normal structures, you'll find that these axial effects are basically 0. But if they're not, then you need to include them in the calculation. But for most normal structures, they're generally very small in comparison to what's happening with the flexural effects. All right. Now, for this, what we're going to look at is that we've got some basic examples to kind of how the method is set up. It's just like what you might imagine. When we got to writing generalized equations, we're going to be repeating that process. So here I have a simple frame that is pinned at A and has a roller at D, and it's a 90-degree frame. So maybe this is a wall or a column, and then here's a girder with some load on it, and the load on this appears to be 1.5 kips per foot. And then for good measure, I've also put a point load at point B, which is the mid height of this column, as an amount of 40 kips. We're going to assume that the beams and the columns, the EI is constant, with E being 29,000 KSI, basically it's steel, and that our I value is going to be 2,500 inches to the fourth. And what we want to find is we want to find the rotation at point C. Okay, now this is different than the beam in that, before we were doing rotations at supports for beams, we just plugged in and looked at the beam and calculated the flexural effect of that. But now this rotation at this point C is also based on the stiffness of the column as well. That's helping to resist it. It's not free to rotate because of the stiffness of the column. So we've got to kind of model this thing a little bit differently. The equations, like I said, are very, very simple. So this video is going to be all about just a couple of examples to kind of illustrate the method. So this should be fairly quick. Okay, so the first thing that we're going to do is we're going to take our structure and we're going to blow it into pieces, break it up accordingly. So the first one I draw is the column, which is ABC. So if I go through and I solve for my support reactions, now I've already solved for those. We're going to assume that you can do that this structure on a whole has a 6.5 kip vertical load at A, and it has a 40 kip horizontal load to the left at A. And then the upper value at D, the dy reaction, is 38.5 kips acting up. So we'll assume that we're able to find those. And with those, now I can go draw shear moment diagrams and start to do my generalized equations. Now, what we have is, if I draw the shear moment diagram, we're going to take this picture and we're going to kind of turn it 90 degrees. And you can see that this is just like drawing a shear moment diagram for the beam that we had. So if we look at our particular directions, if I do my shear, we're going to the left on the shear this way. So then I'm going to go up 40 kips. It's constant over to the point load and then comes back to 0. So if you need some help with the shear moment diagrams, check our other videos for how to draw shear moment diagrams. I'm hoping these are simple enough that you kind of got the basics down. Okay, so that's my shear, and then it's a 0 shear here. Okay, and then if I go and I draw my moment, I start out at a 0 value. It's a positive shear, so it increases up to this value, and then it stays constant coming all the way across. And so in this particular case, the value of the moment at this location is 480 will be our moment. So for our sign convention, we're going to call this as positive and positive for the shear. And so we should be good for that. And then if I turn back, we can go and do the beam in the exact same fashion. Okay, that we know that at the cut line C, and it turns out that the shear at C is actually a 0 value because these two guys cancel out. So there is no shear at C. Okay, and then so we've got, we do have a moment of 480 at the top that we found. That was a counterclockwise moment. And so on the other piece that's connected to it, it has to be the opposite direction. So that's how I know that the 480 here is clockwise. I have my 38.5 kip reaction up at D, and then I have my load of 1.5 kips per foot acting down. So I can now draw the shear moment diagram for that guy. Oh, and then we also have our upward reaction of 6.5 kips because we had a 6.5 kip force here, which was met by one that's down here, which makes this one up. So again, all basic review, you should have no major problems with that. Okay, so if I go through and I draw my shear diagram, we know that it's linear. Okay, so it goes up to 6.5 and it's linear down to minus 38.5, and then that reaction brings me back to 0. We know that it crosses 0 at this point, and you can use proportions to find that. But again, I'm going to assume that we know that value because I want to get into the methodology. That distance ends up being 7.33 feet from the left end to where the 0 is. And that point is important because that's the maximum moment. So now I can draw my moment that it jumps instantly to 480, and then we add the positive area, 1/2 of the 6.5 times 7.33 added to 480 gets me 494. Again, I've rounded the number off, and then it's parabolic back to 0 at the other end. Okay, and so that's our general moment diagram. So this tells me that my beam is going to bow downward, and then it also tells me that the positive moment here tells me that my other beam is going to bow to the kind of inward, if you will. So again, there are those relationships that we've talked about in other videos. Okay, all right, so now that's our real system, and these are our real diagrams. Now we'll have to come up with generalized equations here in a minute. Okay, which is just what we did in the beams. Okay, the virtual system then is just like you would expect from the beams. It follows the exact same logic that if I want a rotation at C, my virtual system is going to consist of a moment, a unit moment applied at C, and then we're going to analyze the entire structure. All right, so what happens in all of this is that if I put a 1 kip moment here, I know that I get a 1/30 kip point load up at D, and I get a 1/30 kip load down at A. Okay, there is no horizontal effect due to this moment. That's my virtual system. So just like we did with the beam when we looked at it, we're going to have to go in and we're going to have to blow this thing apart and draw the diagrams or come up with the basic equations on this. Okay, so all we're going to do is we're going to draw a bunch of generalized equations accordingly. Now, one thing to point out on this, okay, if I go back and I look at my real values, okay, the number of segments that we have to look at have to be able to fully model everything going on. Now, the beam can be modeled with one piece because the line is continuous and straight. Okay, so I need one equation that represents the beam, so I can do a generalized equation there. Okay, but the moment diagram in the column is linear to 12 feet, and then it's constant after that. So I'm going to need 2 sections here and here. Okay, so what I've done is I've defined my x direction as being an x measured from D for this guy, and an x measured up from A for this segment, and down from here for the other. Now, again, it doesn't matter what we choose as long as we are consistent between the two diagrams. So, but that's just the way that I've chosen to set this up. So if I go through and I do this, we're going to cut this thing apart. And so you notice all my x directions are labeled. So from A, I'm measuring up. From C, I'm measuring down. Okay, and then from D on the real system, I'm measuring to the, from the D point. Okay, so that's the exact same as what we did on the other. Those have to match. Okay, if they don't, you'll never be able to get the right answer in your calculations. Okay, so if I go through and I play with my reactions, let's take a look at the beam that's here. Then I can cut the beam, and I know that if this reaction is up, then I've got to have a downward reaction of 1/30 to satisfy sum of forces in the y. So the shear at this point just to the right of support C is 1 over 30. Okay, and then at the cut, I also get the moment, okay, and the moment that will balance this 1 over 30 is actually a 1 kip-foot moment on the end of this beam, okay, because it's 30 feet from here to here, and the reaction is 1 over 30, so that's 1 kip-foot. Now, relative to the cut, if I draw my cut line here, everything on this end of the beam is met by this matching pair in the opposite directions on the end of the joint. So we're going to cut the joint out separately. So we've actually got 3 pieces on this, but we're going to assume that the joint that we're cutting it so close to C that it's basically a point. Okay, so if I plug this in, then I've got a 1 kip-foot here. It was up on this, sorry, it was down on this end for the shear, so it's now up on this end for the shear, because again, they have to cancel on those. And then I can go through and figure out, well, what are the effects happening on the bottom of this thing? So if I sum moments on the joint, do sum of the moments on the joint, I get a -1 for this guy and a +1 for this guy. These two cancel out. There is no moment on the top of the column for this particular calculation, just because of the way this thing is loaded. Okay, and likewise, if you look, there was no shear on the top of the column. That means there's no axial force in the beam. Okay, and then the upward shear on this reaction that was caused by this guy is matched by a downward shear on the bottom here of the joint, which is then, since this is a cut line, is matched by an upward one that is here, which is matched by the downward one in here. So equilibrium is maintained throughout this system. So now all we do is we take our free body diagrams and we draw our generalized equations. Okay, so I've kind of gone through this a little quick. We spent some time setting up these equations in the last video, but for now we're just going to kind of jump straight to this table. But at the end of the day, all we're doing is we're going to break it into the 3 segments that we talked about. So my first segment is AB. My origin was A because that's where I defined X starting, and my limits will be from 0 to 12. So 0 to 12 are my limits. And those were important because those went on to the integral when we start to evaluate our calculation. Okay, the real moment in this equation, so if I take a free body diagram, and so it was 12 feet from here to here, if I go to an arbitrary point X and draw my free body diagram, then the moment in this is 40 times X, right? And you can see that back on the moment diagram that we produced here, right? It was 0 here and 480 here, and it was 12 feet. So the slope of this line is 40, and so the equation of this line is 40 times X. Just like for BC, it will be a constant 40 there. It won't actually vary with a function of X. Okay, now, so that was our real moment, and then my virtual moment, we said when we solved this system up here, we said that there was no moment coming into the top of the column from that guy because of the way this equilibrium worked out. So there's a 0 that happens here for the moment. Okay, BC, we're going to start out, and we said our origin was at C. It's 0 to 12 feet also. Okay, now it's constant. It was the 480, so that's that triangular region that we saw on the picture. Again, that was this guy right here, the 480 back on that first page. Okay, and then we said that there was no virtual moment in this guy either, so that guy is a 0 as well. So then my CD, it would be for the beam, and again, we're measuring from D at this case, so I'm going to cut it here. And so if it's X from here to here, then the moment in this location is 1 over 30 times X for our virtual moment. So that's our 1 over 30 times X. And then our real moment is a little bit more involved, but not too bad. And so what I can do is I can take this beam, and we're going to cut arbitrarily through a point that's here. Okay, and again, we put our internals on it, and if this is X from here to here, it's now going to be 38.5, times an X gets me one term. I have a 1.5 times an X squared is another term, and then we have our constant that solves all this. But you can solve for that if you write the equation for the free body diagram. Again, I'm assuming that we know how to do all that just for the sake of the exercise. So if you're having problems, again, go back and take a look at the video or ask questions in the comments below, and I'll be happy to help you out. So the equation for the moment on this then measured from X is 38.5 times X minus 1.5 times X squared over 2. It all comes back to the free body diagrams. Really, you can't just write that equation from memory by looking at it. You have to draw the pictures. But again, just for the sake of conciseness, I've not done that here. Okay, so that's how you get the real. Now, once you have that, now you just plug into your equation. We want the theta equation for C, so we're going to take the sum of all of the flexural moments. There is no axial load. The axial amount is negligible, so we're going to neglect that in here. Okay, and so basically I'm going to write up my 3 segments. So the first segment is going to be integral of virtual times real, so 40 times, but both of those are 0. So the first two for AB and BC are 0, okay? And then so this becomes plus 1 over EI times the integral then of 0 to 30. So there's my limits. And then it's going to be x over 30 times my value of my real moment. That's what you're seeing here, dx. Okay, and then if I do the calculus and evaluate the integral, you'll find out that theta c is 6,488 kips squared per foot cubed all over EI. Now again, we got to watch our units because E and I are measured in inches. Okay, now this calculation came back as a positive value, so it tells me that my direction on my moment that we assumed for the virtual here is in the correct direction. So positive means that this joint is actually rotating what will be clockwise, and that should seem logical because we have a big load on this that's causing it to rotate clockwise. Okay, and if I do all of that, then we can do our math, and if I watch my units, you'll find out that this is now 0.0129 radians is the angle that thing is rotating. Okay, if we solve for it in a radians value. So anyway, that's all there is to that method. Let's try another one. Okay. Okay, so now I have another one that is a portal frame, okay, in which I am pinned at the bottom at A, I'm pinned at the bottom at D, and then I also have a hinge here in the middle of the beam, BC. So it's kind of a frame, hinge, and then another frame. We're going to put 2 kips per foot at the top, and I'm going to put a lateral load in the amount of 10 kips acting to the right. Now the hinge is located at 10 foot and 10 foot. Okay, so if we go through and we kind of look at it, this is done in exactly the same way as what we did before. Now you'll notice I'm going to cut this one a little bit differently, all right? The span from here to here is 20, the height is 15, E is 29,000, A is 1,000 inches to the fourth, and, or sorry, I is 1,000 inches to the fourth moment of inertia, and then the area is 35 inches squared, okay? And what we want to do is we want to find, okay, our deflection at point C, our horizontal deflection at point C. So what's the lateral sway on this structure? Do that. And in this one, we are going to include the axial deformations on this. So the first thing that I'm going to do is, because this, we could come through if we wanted to, and I could break it into 2 pieces, but you can also, I'm going to show you that we can break this in other ways as well. Okay, and so what I decided to do in this is I'm going to treat the column as one piece and the beam across the top as the other. And the thing that's cool about this is the hinge doesn't matter. As long as I have the end reactions, I can solve this problem. Okay, as we start to solve it, because the hinge's behavior is captured by what's happening in the support conditions. And so it's already being factored in. So if we go through and we draw our free body diagrams of the parts, what we find is that for the full system, the loads that we find is that the upper reaction is 12.5 kips, and we have a to the right reaction of 1.67, okay? And then at D, I have an upward reaction of 27.5 kips, and a left reaction of 11.67 to the left. So I've got 1.67 to the right, 11.67 to the left. This is in equilibrium when I take into account the 10. So 10 plus 1.67 equals 11.67. This thing is in equilibrium. Okay, it just happens to be that I get more shear on the other end because of that hinge and the behaviors that we have happening there. All right. Okay, so if we go through and we draw our free body diagrams, here are my columns, and just like you might suspect, we're going to cut it just below the joint at B, and I'm going to cut it just below the joint at C. So my free body diagram, here are my reactions that we just solved for at A, up 12.5, to the right 1.67, and so if I do a free body diagram of this and solve for all the unknowns here at the cut, I get 1.67 to the left of shear at the top, I get an axial load of 12.5 down, meaning it's in compression, and then I get a rotation amount of 25 here. Okay, and then likewise we can go do the same thing over on the other column, and so we're upwards of 27.5 and to the left 11.67. Okay, now again, I'm measuring X from the bottom on all of these, so that's what these little labels are representing, just so we're clear. Reference is A and reference is D. Okay, and then if I put this into equilibrium and I solve for the unknowns at the cut just below the joint at C, these are the values just below the joint at C. So my shear is 11.67 at the top. I have a downward reaction of 27.5 at the top, and then I have a counterclockwise moment of 17.5 there. Sorry, 175. Can't read my own writing. Okay, so that's 175 kip feet at that location. All right, and then we can go through and we can draw the diagram for the beam. Now again, I've chosen not to separate it at the hinge. No particular reason. It's just you don't need to. Okay, and why make my job any more complicated than it already is? Okay, and so if I have a 2 kip per foot load acting downward at this location, and I plug in all my values, again, all of these reactions here have to be opposite of what's at the top of the column, and all of these have to be opposite of what's happening at the end of the beam also. So that's where all these values are coming from, is from these values at the top. Okay, and so we've got our basic picture. From this, you can now go through and draw shear and moment diagrams, and you can write equations for the pieces accordingly. All right? Okay, so, but that's the real system. Now let's take a look at what we're going to do with the virtual system. So here is, we want a horizontal reaction at point C. So to get that horizontal displacement at C, to get that, I'm going to need a 1 kip unit load acting horizontally at that location. And then we go through and we solve for everything on the virtual system. So this is the virtual picture. And if I do a 1 kip force here, then I get a 3 force down, I get a 3 kip force up, and then I get a half to the left and a half to the left to balance this guy. Okay, and then with that, I can go in and I can find my free body diagrams. And again, I'm drawing the exact same pictures as I did before. So the lower column is here, and we solve it exactly the same way. So we end up with a moment of 7.5 that is counterclockwise, and 1.5 to the right at the cut, and 3/4 up. So this column is actually in tension. Okay, and then if I go and I look at the other side, I have 3/4 up here, which gives me 3/4 down here. So that is actually in the wrong direction. It looks something kind of like that. All right, it gives me that 3/4, and then I get a moment of 7.5 at the top here, and then I get my reaction of 1.5 at the top there. Okay, and so that gets me all their pieces, and then those can go up and parlay into what's happening at the top on the beam. Okay, and again, everything here is opposite everything there, and everything here is opposite everything there on the sign. So you just got to watch the signs and be very, very careful. Now, again, our references are defined exactly the same. A is a reference for this column, D is a reference for this column, and then I'm going to measure from B along the beam across the top for that. So if we go through, now we've got the ability to be able to pull off the parts. Okay, and so AB, my column AB, the height is 15 feet, so from 0 to 15, and we can see that our moment is going to be a linear function of minus 1.7x. So again, all I've done is I've come into, for each of these, if I come back and look at my basic picture, is I've drawn a free body diagram and cut it here and drawn a generalized equation for the internal effects here. And if I do that, the moment and the shears that will happen in all of this are minus 1.67 times x for AB. The F is minus 12.5 as an axial compressive load. Okay, the MV value in this is x over 2. Okay, because again, my reaction here was a half, and we're cutting arbitrarily at a position x. All right, and then my FV in this ends up being 3/4, and it's a positive value because it's a tensile load on this. This column is in tension. This guy is down, this guy is up. This column is wanting to stretch outward accordingly. So that's how I know FV is 3/4. Okay, the BC value is done the exact same way, except now I'm measuring from B, which is the bottom of the beam. Okay, and so, or sorry, my BC is the beam across the top. Okay, so I'm going from B here to B here, so I'm measuring from B, this corner, my beam is 20 feet long, that gets me my limits, and then the moment equation, just like you did before, you can find the generalized moment equation is minus 25 plus 12.5x minus x squared, and then the axial load value is minus 11.67. Okay, and again, that came out of our simple free body diagram. Okay, the virtual moment is now 7.5 minus 3/4 of x. If I take this free body diagram and cut arbitrarily here, I get one equation that will go all the way through here. Now, a test for this equation will be that if I plug in a value of x equals 10 feet, do I get a 0 value for the moment? Because again, or for the moment at the hinge, because hinges do make a value, must have a moment of 0 value at their location. And if you test this equation and I plug in x equals to 10, you do indeed get a 0 value. So that curve goes through the hinge. That's why I didn't have to blow it apart at that location. Okay, the FV value then is 1/2. Okay, and again, if we look at our directions, it's pulling here is 1/2 and it's pulling there is 1/2. That's why it's tension, that's why it's positive. So the hardest part is just getting the signs on these axial loads figured out. And then CD, we can do the exact same thing. 0 to 15, the moment is 11.67x. My axial load is minus 27.5 on the real, and then my virtual moment is x over 2, and then my virtual axial force is minus 3/4. And again, it was negative because this column is in compression, so that's why this guy is negative and the other one was positive. Okay, once you have all of that, now I just plug in to my equation. And you can see that if we go through and we go through the process, it's just a matter of plugging and chugging for all of the members. I'm going to do the axial stuff and I'm going to do the flexural stuff. So let's do the axial stuff first. It's 1 over AE, and it's just simply all of those pieces being multiplied together. Notice there's no integral required on this guy. Okay, so I just plug in all of the axial effects of those three pieces, okay, divided by A over E, and then I can go in and I can do the second term, which is now 1 over EI times the integral of M times NV. Okay, and that's why we get an integral that we have to evaluate. So we're going to wave our proverbial algebra or calculus magic wand and simplify all of this and then evaluate the integrals, and you'll end up with two terms down here. Okay, that 1 times delta C is going to be equal to these particular values. That we have 52,090 kip squared feet squared over AE, or sorry, it's 52.00 kip squared feet over AE, okay, and then plus, I have an equal sign, that's what threw me, but that's a plus 9,375 kip squared feet squared over EI. Now, if you look at this, we have some drastic differences in numbers, but if I do my units conversion and throw in AE and throw in EI, notice that for AE that we end up with a kip squared term, okay, just like we did in our, over on this one, but that the feet term is only a single foot, not a foot squared over on this guy, or sorry, a foot cubed on this guy. Okay, just because of the way these units all work out when we start to evaluate this. Okay. All right, so if I go through and I evaluate these numbers mathematically, this number, this first term, which is the axial effect, and this is my bending, is this term. On here, you can see that there is a drastic difference in the order of magnitude between these. I mean, the axial deformation in this thing is very, 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 very small. It's 5 times 10 to the minus 5th, whereas the bending effects is 4.6 times 10 to the minus 2nd. On this. So this is a further illustration of the idea that in frames, it's the flexural effects that do most of the work. In fact, this is doing something like 95% of the work versus 5% for the axial. It's tiny, tiny, tiny. So if I add these two together, though, the total number is 0.466 on here. Okay, and then if I convert that to inches, you find out that if this was a positive value based on the math, so delta C is equal to 0.559 inches to the right, okay, which is kind of an interesting effect if you kind of think about it. And that should kind of make sense to what this structure would do. The only load on this, well, we had some vertical deflection, whoops, wrong page. We had a little bit of vertical load, and then we had this 10 kip horizontal load that's pushing the structure over. Okay, and so that's why C actually drifted a little bit. Okay, now, if we neglect the axial deformation, we can then say that if C moved over that amount, then this value at B will also move the same amount. Okay, because the axial deformation is pretty substantial. In fact, an area of 35 square inches of steel is a pretty big member, so it won't grow a whole lot in length. That's one of the ways that we know. But anyway, that's how you handle for virtual work for frames. It's exactly like what you were doing with beams. It's just that now you've got to do a couple more steps in order to be able to get these free body diagrams broken into a lot of pieces and then all of the equations on this. So it's not that it's hard, it's just that these methods are very, very long, and you've got to be able to draw those generalized equations like we practiced in the last lesson. But that's all there is to frames. So I hope that's been clear for you. Again, I know it's been a little bit condensed. Well, I say that, it's still 28 minutes into the video, but you get the idea. But it's not hard conceptually, it's just mathematically, it's just a little long. So anyway, if you got any questions, as usual, leave us some comments down below. Otherwise, be sure to like and subscribe to the video, and we will see you guys in the next one. So happy engineering.